All right, so I'm jumping across the introduction because you guys know me. Here's the outline. I'll describe some stuff about particle, argon, and boron. First, with some things that I discovered about interrupt handling that were surprising and led me to an interesting mechanism that Particle has. And then talk about debugging, and then I'm going to do a demo of GDB, and then if there's any time, I might come back to the an adventure I had with some push button switches with some Phantom Interrupt 32, and it does Bluetooth and Wi-Fi, and it has a sister named Boron, which is more or less well, similar hardware, except instead of the ESP32 for Wi-Fi, it has a cellular modem. And between the two, it provides a pair of platforms for a lot of development scenarios. So in working with these things, I had a lot of interesting adventures with interrupts, and found there were a few surprises, and I just want to work through some stuff. I was told that I can't dumb this down I can't dumb this down too far, right? So this is starting from the beginning. What is an interrupt? The best way, I think, to think of an interrupt is like a function call that can happen anytime or almost anytime. If there's no control over whether interrupts are allowed to, whether the CPU is allowed to be interrupted, then it really is anytime. But in the real world, programs have to disable interrupts for periods of time to avoid data races and live locks and things like that. And so the whole game seems to be controlling the, allowing the system, the CPU, to run free as much as possible, but disabling interrupts at critical periods. And let me describe what I mean. Here's a recipe for program misbehavior. Say we've got two statements. A gets A plus 1 and B gets A. But while the code is executing for this statement, and it consists of an add, a minimum of a load, a load, an add, and a store. Let's pretend there's an interrupt right in between the fetching of A and the adding of 1. Meanwhile, code in the interrupt handler has the same two statements in it. So A gets A plus 1, B gets A. And then after the interrupt is done, we come back and we do the plus 1 part of this, and we store a stale value of A. I mean, we're using a stale reference of A. So we end up putting a 1 into B. So B is 1 instead of 2. So that's a classic example of where an interrupt can foul up the execution of your code. So what do you do about that? The fix is to disallow interrupts around the statements in question, and it makes this set of statements atomic. They can't be divided in time. The CPU has no choice but to execute all of these statements because it can't be interrupted. Except on the particle, no interrupts doesn't really mean no interrupts. No interrupts means no pin interrupts. And as many of you know, there are lots and lots of interrupts in an ARM environment. There are all kinds of different interrupts, like, for example, clock interrupts, interrupts to do with A to D conversion, you name it. And so the other, I need to go to the next slide. So the limitation of the Arduino style noInterrupts pair of functions is that it's just a black and white situation. You've either disabled them or enabled them, and you have a dilemma if you can't know whether interrupts are already disabled. So if some containing function has disabled interrupts and has to call your function, and you're executing in your function, and you have some critical sections where you know that other code in your system might execute that same sequence or might try to re-execute your code, then you really have to disable interrupts. But if you try to do that, then when you enable interrupts, you've enabled them too soon. And so interrupts are enabled as you're returning, and the calling code is running to completion with interrupts enabled. And that's a very bad thing. And as I mentioned, with Particle, no interrupts only means no pin interrupts. So I found a better alternative. I was mooching around in the source code for DeviceOS, which is Particle's enhancements or layers of stuff on top of free RTOS. And they've got they've put a lot of work into compatibility with Arduino code. And down in the wiring section, right alongside the code for disable interrupt, which is a commonly used function in Arduino land, right alongside that is this fantastic class called AtomicSection. And it's a C++ class. And when you instantiate an object of this class, it captures the current interrupt state and disables almost all interrupts. And by almost all, I mean all the ones that you can practically disable. There are a handful that you can't. One appropriately named non-maskable interrupt that you can't disable under any circumstances. And then there are other interrupts like divide by zero and memory faults and so on that are typically excluded. But it does include things like clock interrupts. And then when the object is destroyed, its resources are returned back to the system, just before that happens, the old interrupt state is restored. So now you have a case, your code looks more like this, and you have a declaration of the class, and this is the name of the variable that will be an object of this, an instantiation of this class. And the way C++ rules and work is that when you have a new function, or if you just have a block delimited by curly braces, it creates a local scope. And within that local scope, the lifetime of this object is only the same lifetime as the curly braces. And so what it does is it creates an object called lock before executing the body of the function, and then just before returning from the function, it destroys lock, and the function, and I'm going to show you the code for this, and just before that happens, it restores the original state of the interrupt state. And so if it had been locked, now it's unlocked. If it was already locked, it stays locked. And as I mentioned down here, you can make your own block anywhere you want to. So if you've just got a few statements that define a critical section that must be dealt with as an atomic set of operations, then you can simply put in a curly brace, declare your little atomic lock, and you'll notice, well, actually, this isn't clear, but you can have as many of these as you want to, because the scope of this name is only within these braces. The name lock disappears from the compiler's consciousness, so to speak, as soon as you get past this closing curly brace. So farther down, you could have another open brace, rename the same name, there's no conflict, and it all just does the right thing.
Yeah, Pete, the name for that in C and C++, it's called a compound statement, what's in the curly brace. So really, most people don't realize this, but a function only takes one single statement, and the curly braces basically allow you to create what's called a compound statement. So what you're talking about is the scope inside the compound statement.
That's correct. Yeah, so you're basically creating a local scope that is within the span of these braces. And so in case it wasn't clear, this is what the code looks like if you, and I'm going to show you what this actually looks like later on. But the code for that function has a behind the scenes hidden call to the constructor, and then here are the two statements, and then there's a hidden destructor call. And I've already covered this, the scope issue.
So this doesn't really work like standard mutexes then.
This has nothing to do with mutex.
Yeah.
This is not. It's this is about interrupts, and mutexes are a different animal. This is strictly about controlling, holding off interrupts and re-enabling interrupts. So here is the code, the massively complex AtomicSection source code. As you can see, here is the constructor, and all it does is it stashes, it calls this hardware abstraction layer routine to save, well, it disables interrupts, but it returns the previous state, which is parked in this integer. And then in the destructor, the previous state is used to re-enable interrupts. Well, if the interrupts were already disabled, then they stay disabled, right? And so it handles the dilemma that you have if you don't know if you're in an interrupt or not. I think that it would be very easy to implement this class for vanilla Arduinos and other flavors of ARM Arduino environments. And it would be I think it would constitute a public service. So the advantages are you don't care if you're inside an interrupt handler, and especially on Particle, if there's another interrupt like a clock interrupt that might be driving the thread scheduler that would cause another thread to be scheduled that happens to run those two statements, you don't get screwed. So this was the motivation. Next section is about debugging. Some of you have had experience with debuggers. Some of you rely on print statements, and I'm going to describe a debugging environment that's been around for a very long time that's hiding under the covers in the Particle integrated development environment, which I'll show you in a minute. So in the typical scenario, we have a problem with our code, and we scratch our heads, and sometimes we can kind of imagine and realize what the mistake was and go in and fix it and recompile it, and it works. And other times we don't have any clue, and so it's natural to start figuring out how to get the information out of the code, especially if it's not doing anything. It's not putting wrong output out that would give you a hint. You know, if all of the ones are zeros and the zeros are ones, it gives you some information. But if you don't get anything out, then you naturally put print statements in. But there's a different approach that's possible using a thing called a debugger that has capabilities that allow you to not just extract information, but actually monitor the flow of the program, and actually detect references and so on. So you can control the program execution. You can start it. You can, while it's running and it's sitting there wailing away, you can type in Control-C and interrupt the code, look around, decide to run it some more and do a continue, and it will continue running. And so you can arbitrarily control the execution. You can also stop at any one of a number of places. There's typically an implementation boundary on the number of places that you can stop. In this case, I think it's 6. It controls what are called breakpoints, which are points that you define, such as line 146 of inside function foo. And when control gets to 146, before it executes that statement, it stops and control comes back to the debugger. You can inspect variables, including very complicated variables. GDB understands C++ syntax, and so you can have all manner of complicated nested arrays in structures of arrays and so on, with subscripts, and type in expressions, and it will show you values. You can also run the program a step at a time, a statement at a time. You can also step over a function call so that you don't step into the function call. You can also see where you came from. So, like in the case of a loop, like if you know that your code is hanging, you can just start it up and start running, interrupt it, and do an info space S for stack, and it will show you where it's executing, who called that function, who called that one, and that one, and that one, all the way to the root, to the original starting point.
The full stack. Yeah.
The full stack down to some never land, depending on whether or not you're running a thread or if you're in the system, the operating system, and so on. You can also you can watch for changes of variables, and that is really powerful. You can basically say, the next time variable foo gets changed, I want to see exactly where it's happening. And you start your program running, and it traps, and you see, well, actually, it shows you the statement immediately after the reference. And so you just look back one statement, and by golly, there is the amazing, surprising way that the variable got changed that you had no idea was possible, but now you do. Also, one of my favorite capabilities is that GDB allows you to execute a function and print its return value from an arbitrary place. You can run your code from wherever you are. Basically, the limitation is that it has to be visible. In other words, you can't execute a function that cannot be reached from your current code, but that's very seldom a constraint. So you can literally have your own print statements anywhere you want them. And if you've got some functions that will dump out information about your program in a convenient form, you can execute that anytime you want to. And I find that to be quite an amazing feature. So my adventure with GDB was a side effect of the fact that the Particle Workbench, which is the name of Particle's integrated development environment, it has a very fancy graphical user interface, but it's pulling this. It's implemented with GDB, and so the user of the GUI has a really nice, sweet interface that shows their variables. They see their source code. They can just click a breakpoint into their source code, run to the breakpoint. They can have windows that show the values of their variables and so on and so forth. And it's all fantastic, but it doesn't run on the version of Ubuntu Linux that I use. And I went around the bushes with Particle support staff, and they assured me that it worked on Linux. And I assured them that it didn't work on my flavor of Linux, and we didn't get any, there wasn't any progress with that. Well, partway through that, I discovered, I got a clue about how Particle Workbench was running GDB. And I just went in and I hacked some stuff together, and I made a script or two. And so I run GDB alongside Particle Workbench. And I'm going to switch to that. Okay, so this is the, let me see if I can. So
Status.
notice this, Particle Workbench is a plugin for Visual Studio Code. As a person who hated Microsoft for many, many decades, I have to go on record as saying that it looks like Microsoft is changing their stripes. Visual Studio Code is released with an MIT license, and it's really nice, and the price is just right, and it's a nice piece of code. And I have heard rumors about the guy that created this program and or that wrote the original version of it, and looks like there's a sea change going on amongst some portions of Microsoft. So anyway, I like it, and Particle Workbench is a plugin, and as you can see, it allows you to see your source code. It has an area where output is shown. It shows you as was said, the source, the tree of files. Mine is completely flat. I am a very lazy person, and when it comes time to structure some of these components, and we decide that they should be libraries and they should be in their own little directories and all, cute and everything, then we'll do that. But for right now, it's just flat. So here, this little button here, so if you're using Mac OS or Windows or the right version of Linux, and I assume that's a vanilla Ubuntu probably, here is the debug button. And when you push that, if it hasn't already, it builds a debug version of your code, and it puts up the VCR-like controls for playing and stopping your code, an area over here for showing variables, and so on. But I can't use that. So instead of that, I'm using this. So I wrote a little script that looks like this, and all it does is it's very, very dumb. It's hardwired to a specific version of DeviceOS. It's hardwired to the Argon versus Boron platform, but it figures out where your project is, where your code is based on being executed inside your project directory, and it runs this little script, which looks like this. And this runs a program called OpenOCD, which stands for On-Chip Debugging. And this is a piece of code that talks to the particle hardware debugger software. What is it? Serial wire debug, SWD debug dongle. And the dongle plugs into USB, and then another connector plugs into the argon or boron debug connector. And it talks to OCD, and OCD talks to GDB.
It's not
And
a
it
JTAG, is it?
It's SWD.
Okay.
Yeah, it's effectively JTAG. Yeah, and it talks on port 50,000 using local area network sockets, and so when I run this script, it starts OCD in the background, and then just on its way out, it wipes out the OCD open OCD instance. And so now this is GDB has started up, and it's loaded the symbols out of the executable, which is alpha-code.elf. And I can, GDB uses the minimum abbreviation for all of its commands, and they spent a lot of time arranging for you to do a great deal of stuff with single letters. So L is short for list, and here's a function called handle FX interrupt, which is the interrupt handler for the 6-axis sensor chip that's being used. It's the NXP FXOS 8700 accelerometer magnetometer chip. And so this is the function that the C++ function that gets called with that interrupt. And I would point out the fact that this is actually a C++ function, not a C function. The particle guys put in the extra work to extend attach interrupt, so you can pass it the function specifier and a this pointer. The this is the C++ magic word for the pointer to the current object. So you can pass an object that implements the function to attach interrupt. That is fantastically powerful, because now inside your code you can do C++ things. You don't have the pain in the butt that is brought about by being constrained to this being a C function and not being able to, it involving a great deal of pain to be able to access other parts of your code. So anyway, this is the function, and what I thought I would do is put a breakpoint I'm going to put a breakpoint at begin, which is the initialization, and that brings me, oh, I just remembered something else that I wanted to show you. This is the chip initialization code, and I'd like you to point out something that you might notice if you look at this closely enough. Do you notice anything interesting about this code? This is putting values into the chip's registers. Do you see any hex numbers in there, guys? You see any 0x56s or 0x2As or any of that garbage?
You'd probably pound to find your literals.
Instead, it's all symbolic. And not only is it just vanilla, there's a set field macro, so you can use, you can set multi-bit fields symbolically. So this is setting the rate at which the chip samples when it's asleep, and this is the rate when it's awake. And those are set into the field ORed in with other bits, and then written to the register. And it's not hard to do, but it does take time. And a nice side effect is that it makes you more and more familiar with the datasheet of the chip. And this particular chip is killer. It has 78 hex 78 registers, has 120 registers, and a lot of flags. So anyway, so we've stopped here, and now I'm going to type a watch command on this variable, global variable called interrupt count, and then I'm going to do a continue, and we notice that we've got a trap right here, and it's on this program statement. And if we do a list a little bit ahead of that, there is the statement immediately before the one that we're shown. And oddly enough, it's an increment of global variable interrupt underscore count. Again, it's sweet. This is a very, very powerful feature that can save you enormous amounts of time for certain kinds of bugs. I can just show you the single stepping that I'm going to do, where I'm stepping across this function call so that I don't bore us. And you can print out, actually I think it's mag interrupt source. Print out the values of variables. In this case, these are the two interrupt source bytes, and each of the bits of those bytes corresponds to a particular flavor of interrupt for the chip. So this particular chip can interrupt on 3 different situations involving the magnetometer. Either the vanilla one that says there's new sample data available, or one that says that the values of the axis the axis values have exceeded a threshold that you specify. And there's both an and an or situation with those that you can have. And then there's a third flavor where for each sample of magnetometer values, it computes the vector magnitude, and you can interrupt when that vector magnitude exceeds a predetermined limit, which is very handy for certain applications. The interrupt source pertains to the accelerometer, and I should say this chip is I've forgotten the part number of the predecessor Freescale chip. That this chip is a magnetometer glued on top of the Freescale chip that, if I could remember its name, most of you would probably recognize the part number. It's been around for a long, long time. So the interrupt source goes with the accelerometer causes, and there are a bunch of those. I think there are like 6 or 7 different flavors of interrupts to do with accelerometers, and you guys have probably heard about them, like tap detection, double tap detection, and again, it has a vector magnitude mechanism that can be very handy, where you don't want to have to be constrained by an orientation. You want to just know that, hey, this accelerometer, this chip was accelerated greater than X. Greater than some acceleration, and you want it to be orientation agnostic. And so the vector magnitude is really good for that. Here's some more of this code. And if I go down to the code for the data ready, which is the vanilla sample code, this function is an example of one that requires a critical section. And let me put a breakpoint on 844, and we'll continue executing. And I'm going to step into this function And here it is. And notice our old friend AtomicSection lock right there. So right after the preamble code of this function executes to save registers and make space for locals and stuff like that, it is saving the current state of the interrupts situation and disabling interrupts. Now, this is actually larger. It probably doesn't have to be the entire function. I have not bothered to optimize this. Entries is a word-sized volatile that doesn't have, there isn't any lack of atomicity, if that's a word. So it's probably safe. But down here, when you're starting to mess with the storage, this is a FIFO ring buffer, and especially when you're messing with these indexes and the count of entries, that's the kind of thing where you positively, absolutely don't want some other thread of control coming through and executing that same code. Likewise, you don't want any code that is operating on those variables in any fashion. Let's see. If we step, let me get. Here's the stack trace. So as you can see, we're in put data. We were called from handle fx interrupt, and here is all of the stuff that was called prior to getting into the interrupt handler. And it is for sure the case that C++ incurs a lot of overhead that C doesn't. And it's hard to argue with the fact that there are many routine calls here to fiddle and figure out how to get to the specific function. But this is not a performance critical application. In fact, it's on the other end of the known universe from a performance critical application. And so the fact that it's 10 layers of calls deep to get to this interrupt handler is absolutely irrelevant. Doesn't matter. But now if I put the frame, if I do a frame command and go back to frame 1, I'm back in the call to put data. And if I put a breakpoint, whoops. Oh, that's not very convenient. Oh, let's put a breakpoint down here, 856. And I run to that. I can now execute a function that's in the rig buffer class called available, which tells me how many buffer entries are actually used, how many are occupied. And we can see now that it's stored, it's called put data once, and now we can see, and that beats the heck out of going in and figuring out where those, well, in fact, looking up and finding the details. If you know that you've got a function that puts the information out, you can just call it. I think I've covered most of the features. I've covered most of the features that I used. As I was showing Shane, this debugger has about 200 or 300 or 400 commands. It's ridiculous. It makes Emacs look simple, but I get along really well with about 6 or 10 commands, and it is a tremendous tool to have available. So if you get involved, sorry?
GDB has been around for many years.
That's
I
right.
probably used it 30 years ago for stuff.
Yep, absolutely. In fact, oh
There's
shoot,
a GUI interface for it called DD or
yeah,
DDD. I can't remember.
yeah, I'm not on the right machine. I thought I had a little C++ program so I could show you GDB running on the Linux system, and it looks the same, behaves the same, and as Carl said, there are lots and lots of convenient front ends for GDB. Particle, as I've just described, is only one of buku convenient interfaces. Let me find my way back.
Another little side note, the commands for GDB are the same commands you would find in the Python debugger.
Nice.
They're
They're
based on the
almost
same.
identical.
Yep. They're based on the same. Well,
Yeah.
one was kind of a fork to the other, but not quite a fork. It was
Yeah,
a draw
GDB
from
was
the base of
probably
one.
the mother of all of them, but
Yeah.
everybody has copied it.
Actually, I could say I would have to assert that the GDB was a copy of the BSD debugger, whose name I can't remember, but I think it's 3 letters. No, DBX. Yeah, it's 3 letters.
Yes,
DBX.
yes. I was just going to say that.
Yeah, DBX was a slick, fancy layer of stuff on top of a more primitive debugger that goes back to the mid 70s, or maybe late 70s. Okay.
But the big claim to fame on GDB was it was the first one to be able to do remote debugging of another device separate from the terminal that you were on.
Yes. Okay, let me go through this second one, and then we can discuss stuff. I'm about to describe something that doesn't make any sense, but my oscilloscope is pretty good, and it doesn't lie. And so here's what's happening. So I've got these bog standard switches, and when you press one of these switches, it grounds the signal pin that's connected between the resistor and the switch. So it directly connects ground to the pin that's going to an interrupt on the MPU. And when you let go of the switch, this capacitor is charged up, and while it's charging, the voltage is increasing from ground back up to the supply voltage. And the timing of the 3K resistor and the 100 nanofarad cap comes out to a very, very quick rise time. And it seemed to work great until I started pressing on the first switch and began getting interrupts on the second interrupt line. And if I press on the first switch enough, I get interrupts on the third interrupt line.
Now, I presume these are debounced switches?
That's what you're looking at, is the debouncing hardware. This is the debouncing circuit for the switches.
Okay, well, I'm used to a little bit more complex debounce circuit than that.
Okay, well, it works if you look at the if you put the scope on the switch that you're pressing, the scope is currently connected to this line right here. If you set it up to trigger when you push this switch, it's absolutely fabulous. It goes from 3.3 volts down to ground in about a microsecond, and it sticks there like glue. But for some reason, actuating one of these switches causes a transient, and here's what it looks like.
I have a comment there. How close together are the wires?
That's a good
at the point where the capacitors are connected.
Excellent question.
The reason
I
why I'm
figured
saying
like
that is that you're creating an inductive pulse that's getting onto the other inputs, interrupts.
I think that that's probably what the problem is. Unfortunately, the quick answer is that I've tried this with everything between, the wires where the individual jumper wires are all kind of stuck together. I've tried it, and it ran through my mind like, oh man, these things are right alongside each other. They're one that's inducing current into the other, blah blah. So I separated them all out so they have inches of air. However, these wires from here to here are about 10 inches long.
Well, there
So
you go.
Nice antenna.
Yeah.
Watch this. There's a freight train driving past.
Yeah. We can hear the train going by.
Okay. This is switch 1 being released. Notice how slow it is. I'm sorry, this is switch 1 being pressed. Notice how slow it is to go down to ground. It's 20 microseconds per division, so it's taking about 80 or 100 microseconds to get to ground.
That's the capacitor.
No, it's the inductor. I'm pressing the switch. I'm pressing the switch. So I'm connecting the switch to ground, but I'm wondering if I'm having to charge, if I'm having to build a magnetic field in the wires going to the microprocessor. In other words, there's inductance in the wires, and so it's momentarily presenting a high impedance and then lower.
Yeah.
Okay. But look at this this is interrupt 2. Do you see that little yellow line right there?
Yep.
All right. This is 20 microseconds per
induced right across it. Yeah.
It's 20 microseconds per division. Here's 20 nanoseconds. And that's where it triggers the MPU right there. So it is the second interrupt line is glitching, and I don't really understand the mechanism.
Well,
I will say this, Pete. What I'm used to doing is a pair of NAND gates acting as my switch debugging circuit rather than an RC.
Yeah.
Sure.
I was just going to say, Scott's suggestion before of having a little bit more of a sophisticated debounce circuit may solve that problem.
Yeah.
Right. But the funny thing is, I've seen this debounce circuit, this bog simple debounce circuit that I just described, at least 1,000 different places. It is so common.
But the
it's
timing
ridiculous.
of it is usually set for a good 1/10 of a second or so.
That's probably it. It's too fast.
Right.
Right. So the timing, the combination of the resistor and the capacitor values are wrong or whatever. So what I did was I pulled
your best bet would be to take the one of the switches sometime, disconnect it from any other circuit, connect it right across the scope, and you'll see how long that the bouncing on that switch is going for you. And you'd be surprised how bad these little suckers are, because they're usually carbon contact plates.
Well, this is why I wanted this thing to jump on it and hold it to the ground with extreme prejudice. And I think I got it a little bit too aggressive. But I simply removed the capacitors and switched to software debouncing.
Have you tried scoping it with the MCU detached in case there's something unusual happening on the inputs of it's supplying current or something through the MCU?
That's another good question. I haven't tried that, and
that'd be my next question too.
That might be interesting. But just to summarize this, at this point right now, for me, this is academic. If if I revisit this, I will do exactly what you're recommending, and that is design the time constant to be appropriate to the specific switch. And I've seen switches like you were saying, Scott, where the thing bounces for multiple milliseconds, many milliseconds. So
Hundreds of milliseconds.
yeah,
I've had a switch go as far as 200 milliseconds before.
That's amazing.
It was a heavier duty toggle switch, but it was the kind that was used in the space capsules in the Apollo program.
Good grief. Yeah, my solution was to basically, when I take the interrupt, I stop looking at the interrupts for the debounce period, and then re-enable them. Well, that's all I've got. Here's some information. Again, let me type the URL of the slides in while we're talking.
I'm trying to think. What is it? That's not a which NXP chip is that called?
DeviceOS 8700 CQ.
I know, but there was a general name for that, a layman's name.
I'm not familiar with that.
It was sold through the various kit stores like SparkFun and then Elector Magazine and all those guys.
Yeah, Adafruit. There are lots and lots of the providers have provided breakouts for it. I have never seen it called with a special name.
On the circuit board that you got these switches mounted, how expensive is your bill of materials or the cost of putting the layout on to add like a pair of gates? You know, if you put one chip of 6 gates or so on there, and you can use those to act as your debouncing circuit.
So this is strictly a development prototype. So it's a solderless breadboard. The target product will only have one push button switch. It already has one. So the boron sits on a carrier board, and the carrier board has a push button switch, and it's not actually even used as a momentary switch. It's used as the system has started up, and we have noted that the switch was being pressed while the system started up, and that's the end of the lifespan of that switch. I look like I'm in a ghost movie or something. Oh well. So there isn't really any need for the debouncing in the target. The interface to this system, you might be interested to know, is via cell phone, smartphone apps. Particle has these magic variables that can be set and read across the internet. So when you set one of these variables to a value, some period of time later, that value is reflected on the internet. And likewise, it can pick up an updated value that's been set on the internet. And so the typical user interface for a particle system is a simple little app or a generic app that's just smart enough to set and observe these variables running on your smartphone. The boron in particular has Bluetooth, and so these little apps can run on your smartphone and talk to the boron via Bluetooth and go directly and bypass the internet. So there might be some considerable current. Or no? Are you implying that there's... Oh, yeah. You mean from the top of the capacitor down to the switch? Yeah, I get you.
So for the recording, I'm not sure if it gets the chats, but Shane's comments was, I think the glitch on the debounce is due to divide by 0. Voltage on cap divided by the switch resistance, which is now 0 having closed the switch. So Shane's suggestion was to put a small resistor in series with the switch.
Right. So then when you press the switch down, you can't charge the cap any faster than a certain rate, and it eliminates. Okay, so well, if I had discussed this with Shane before the talk, there would have been no point in bringing this whole thing up.
Yeah, but then none of the rest of us would have learned anything.
Well, I guess that's a good point. I should point out that if you look on images.google.com for hardware switch debounce, you will see hundreds and hundreds and hundreds of schematics that look just like this. But the choice of values is
left as an
probably
exercise.
also a factor.
Yeah, left as an exercise to the student.
Well, I'm assuming that a much smaller capacitor.
I was going to say one of the reasons you see so many circuits that people assume works because the Arduino, the 328 processor, actually has dedicated Schmidt-triggered debouncing built into the hardware.
Right.
So
Nice.
circuits that won't work anywhere else work with that. So people build cruddy circuits and think, hey, they work. It must be a good circuit.
There you go. And people like me look at it and say, geez, there's 1,000 of these. They must all be right.
Got to check
Okay.
references or sources.
Yeah, where I learned my switch debouncing wasn't even with an MCU. It was with just straight pure TTL circuits. And you actually put that on the scope and you can actually see what's going on.
Yep.
Yeah,
Very
you
good.
can use JK flip-flops
The
and
JK flip-flops, the 555 chip used in there. I've seen regular op-amp debouncers.
yeah, there's a bunch
You
of
may
different ways to do debouncing.
You may recall Brian. What is Brian's last name? In Wilson.
Right.
He used to come to meetings. And he made a switch circuit using a pair of NAND gates that were cross-wired.
Yep.
Exactly. That's the one that I tend to go to. That's my little go-to debouncer.
Yep. All right. Well, I got an education on that. Shane, when you wrote divide by zero, I thought you were kidding, and it took me a second to read the next couple of statements to start making sense out of that.
And if you're wanting to dive deep, Jack Gansel has a couple of great papers on stuff that he put into research that he did with switches and doing switch debouncing, and his stuff on that and Watchdog timers is pretty awesome. Let's see, I'll stick a link in for the first one, and the first one has the link to phase 2.
Very good. Let's see.
The divide by zero makes a lot more sense if you've ever accidentally dropped a wrench across a car battery. That's dividing by zero.
One other adventure that happened with the particle that kept me going for a while was when I was I was using C++ incorrectly, and inside a function I said previously declared object variable name gets and put the constructor on the right hand side of the assignment, and instead of instantiating on another object and assigning it to the variable, it calls the constructor and then calls the destructor immediately afterwards. And I didn't discover this until I didn't show you guys the fact that you can disassemble your code and look at the machine instructions. And something led me to disassemble this function and there was the call to the destructor immediately after the call to the constructor. And the call to the destructor zeroes out the buffer pointer. And so subsequently trying to use that buffer resulted in references to low memory that had protection on it, and it was causing a hardware fault. But the particle interrupt handler for the hardware faults was beyond incompetent. And I could never get a clue looking at, I must have looked at about a zillion stack traces stemming from the what looked like, it looked to me like the wrong interrupt, the interrupt handler was being called inappropriately, and that was intermixed with the switch debouncing, where I was getting free button 2 interrupts. And I initially was looking at the code, and if you look at the low-level interrupt handler for the pin interrupts on the Particle with DeviceOS, it only has one interrupt for all of its pins. And it runs around in a for loop answering the question, well, did this pin cause an interrupt?
Was it you?
Yeah, was it you? And after cleaning the vomit up off the floor, I was not impressed by that. In my mind, that's why you have an interrupt vector table that's got like 128 or 256 places where you can just go directly to the handler. But anyway, I was completely faked out chasing after this, which ended up being bouncing of the switch buttons, and eventually by accident found that the whole thing was caused by the attempt to store through a null pointer. And it was causing a hardware fault, but the hardware fault was very well disguised. I now know that it was somewhere back there on the stack, and if I cared, I could probably reproduce it and go back and figure out where on the stack the hardware fault handler vector, the vector for that interrupt, it was basically at some point there was going to be the code address of the statement in my code that was saying null pointer gets value, and the hardware was saying no, you're not going to do that. We're going to interrupt. But I'm growing to appreciate Particle. I think that the company is maturing. They're hiring, according to Chip McClellan, they're hiring more and more talented and senior staff, and they seem to be maturing as an organization. I think DeviceOS is reasonably solid. As I say, it's based on free RTOS, and it has the stuff that you would expect of an RTOS. I don't know how. I'm sure that there are ways to measure the performance of RTOSes, but as I explained earlier, we don't have any performance issues. In fact, this particular device spends 99.99999% of its time sleeping. And then there's an accelerometer or a magnetometer interrupt, and it wakes up for a fraction of a second and then goes back to sleep. So it's not very critical.
Pete, I got a question for you about the function that was calling the destructor right after the constructor.
Yeah.
Were you using that variable in the same method and it wasn't working, or were you using it elsewhere?
I temporarily lost my mind about how to declare a
Global.
class, how to instantiate an object, and I'm trying to figure out how to show you what I did. But basically, so you saw the example. You saw the example of atomic section, right? So it was atomic section, open close paren, variable name, semicolon, right? And if the constructor had parameters, it would be in between those parentheses. And I was saying lock equals atomic section, open close paren, semicolon. And for reasons I do not understand, the compiler, in fact, actually, I could just imagine the compiler developers saying, we're going to train people out of this. We're going to make this as painful as we can make it. How could we make it super painful? Let's emit code to call the constructor redundantly, and then let's call the destructor. All I can tell you is that that's the code that comes out of the compiler for that statement. So shall we just throw it up open for any other discussion, or anybody have anything to share?
Nothing from me.
I don't.
Well, I'm working on a TFT display that's going to control a battery charger for lithium-ion batteries. For that battery pack I flashed up on the screen about an hour ago. It's a charger that hooks up to that thing and will allow it to charge either 3, 4, 5 cells. It's a constant current, constant voltage source. You still need the BPS on the battery. I mean, it doesn't do any BPS stuff, but it does give you a constant voltage and a constant current, because you don't want to over voltage the BPS. Otherwise you fry all the MOSFETs on it. So,
Do you ramp down your
things.
charge?
2 little push buttons, you can change the voltage, and another push button will lock in the standard charge for lithium ion, which is 1,250 milliamps, or you can flip it to adjustable and use a pot to adjust it. But yeah, so it's kind of cool. I've got it mostly working. I just ordered the boards today. So we'll see how it goes.
I've been playing around lately with some digital potentiometers, and I'm trying to get them to work the way I expect them to. They're not cooperating with me.
Which ones are you using?
I'll have to look at the part number, but I ordered them from DigiKey, and based on their little drill down, what are you looking in this, that, and the other, what specs, and I'm thinking what I'm discovering is that these damn potentiometers are polarized, and I'm looking for a non-polar. I need it non-polarized in my circuit.
Well, you got the data sheet on it?
Not
What's the
handy
part
right
number?
now. Not on this computer, but yeah.
You know what the part number is?
What's that?
You know what the part number is?
Not handy. Not on this
Oh,
computer.
okay.
I've used the analog devices, and I can't remember the part numbers off the top of my head, but they are not polarized. And they use SPI, and you just poke the number in, and the resistance changes very, very, very quickly. I can send you the part numbers of the ones that I've used, and they've been very, very easy to use, very straightforward. The only trick is you have to watch out for the power dissipation. They're very, very low power. Oh,
Okay.
Also voltage. They have voltage limits too that you have to watch out for.
Yeah, what I've seen some other circuits people doing is they'll feed the electronic potentiometer into an op-amp circuit and use it to drive the current change and stuff.
Yeah, I don't have access to my parts database at the moment to bring up the part numbers, but I'll send them to you. As I say, they're analog devices, and I think they make a higher voltage flavor also that can stand a few tens of volts.
You can use an R2R ladder and just that's what most of the DACs, the low-speed DACs use. And that you just shunt one of the resistors to ground or not, and that'll give you easily 8 bits. And there's a look for the 2-quadrant or 2-quadrant multipliers. A DAC 08 you can do it with which is an ancient part, and just put a resistor on the output, and that'll give you 2-quadrant multiplying.
Yeah, I didn't even think about using this because in the circuit I just mentioned, I have to switch in and out some resistors to change the voltage, all done through the CPU. And I'm using digital switches. They're actually MOSFETs in a 6-pin dip, similar to the dip that this is. But
Yeah, well, as I
I don't
said,
have them yet, so I haven't really tried getting the whole thing to work.
The power dissipation of these little digital pots is minuscule, so you'd have to.
Well, I'm just
you
switching
might
in
have
and out
problem.
resistors that are controlling an op amp, and that op amp controls the actual voltage. So the current through them is going to be very low.
Right.
That's what I've seen. Yeah.
I think
Remember,
I'll turn
your
my
op amp, you're working as a voltage controlled current source.
Yeah. It's so I found a circuit which I've modified a little, as I always tend to do, that not only gives you current regulation, also gives you voltage regulation. Does both for you. But it's a linear circuit. I thought about going to a switching power supply, but man, that was like 20 times more complicated. It was just easier to build a linear out of it, get a transformer.
I've been
There's the transformer.
I've been playing with some FPGAs. There's a cheap one which is complete with USB and got like 32 I/O lines. It will do 200 megahertz and it's $5 a piece, which is pretty impressive. It's got about 700 logic units on it, which you can do some pretty intense stuff. And then I have one that has 18 DSPs on it, and close to 100K of memory. And the DSPs will do 4 or 5 nanosecond multiplies. Pretty impressive chips for $20. So if there's any interest, I can go through sort of my experience using the tools, and at least on the $5 part, and sort of demonstrate what it can do. But you've got basically probably 10,000 gates on this $5 chip that you can program to do whatever you want. Add, subtract, multiply, divide, accumulate. They're pretty impressive, and the timing generators are down in the picosecond range. So for $5 you get the board, the chips, and everything. So I can I'll happily go through that if somebody wants me to.
That sounds very interesting, and if you'd like to claim the November meeting for that,
I can go through that in the November meeting.
Terrific.
I got them. I have a digital light projector that I'm using in a particular project, and I got them to be able to generate certain specific test patterns. on a digital light projector. I've been toying with the idea of creating a little board that fits under an ESP32 with a FPGA, one of the ones with 18 or 20 DSPs on, so you could just sort of turn it on and you'd have something that was incredibly fast, and then turn it off and you're back to low power mode. I'm not quite sure what I'd use it for, but it's an impressive idea. But I can go through. I'm using there are dozens of companies. I'm using a particular Chinese company because their stuff is cheap, and they're actually very responsive. I'll claim the spot and do that.
Terrific. And actually, on this subject, some of you might have seen the email from Charles Lord. He said something to the effect that SparkFun has backed out of making the radar breakout board. That he's been.
Yeah.
I don't know whether that implies that he's not going to be able to give a talk or not. I will follow up with him on that.
I have probably 20 moderate power radar boards sitting in a box. I have a lot of boxes. So it's a if he wants them, then we can talk. But these are, then he was working in the 10 gigahertz range. These are like 5 gigahertz devices. I have some 10 gigahertz devices, but these are Doppler shifts, so they only work on motion. But you can, if you use. I was playing with algorithms where you had 2 or 3 units covering an area, and you could work out when somebody moves, what direction and how fast they were moving. So you can basically from the Doppler measurement, which is the first differential and the second differential, you can work out position if you want to do some obscure mathematics. As I say, I got this nice 5-digit National Instruments 5-digit PCMCIA slot digital multimeter card for like $30 on eBay. It's ancient, but it's 5.5 digits and 60 hertz conversion. It took a little futzing to get it was designed for a DOS system, so I had to futz the device drivers on a Linux system. But I've got it running in Python, so I can. It's a 24-bit AD converter, which is a lot of bits. And for $30, I saw it come up, and I said, nobody bid on it, and so the last 10 seconds, I put in my bid and got it.
I think this laptop still has one of those slots.
Yeah, no, I've got an ancient ThinkPad. I've got more than one ancient ThinkPad, and just if it does nothing but act as a voltmeter, a recording voltmeter, that's quite reasonable. And it does resistance, voltage. With a shunt, you can do current.
So
I was quite happy with it.
Is it those side cards that plug into the?
Yep.
Okay. Yeah, I've got an old ThinkPad with one of those in it too.
Oh yeah, no, it's. But yes, it's nobody nobody's old enough to remember how to use the cards.
Yeah, well.
So it's there's a certain advantage to being ancient.
Believe it or not, I believe this laptop even has a Windows XP partition still on it.
Yeah, I haven't quite. I do have a machine with a Windows 10 for one of my spectrometers, but generally, it's most of my world is Linux.
Me too. I haven't fired up that partition, I don't think, in like over a decade.
Yeah, I've got an XP virtual machine running on a headless machine here, but I don't use the machine too much at all. The Linux, it's a Linux machine with a XP VM on it.
Yeah, I've gotten a fairly expensive optical spectrometer, which happens to want to run on a Windows machine, and I'm not. I couldn't afford to replace it, so I keep a Windows machine just for that.
So right, I have a working Windows machine that I keep just for updating my TomTom. Which is weird because TomTom is running Linux, but do you think they'll let you update it on a Linux machine? No, has to be a Windows machine.
I have two NVIDIA Nanos, which are the DSPs, the things you use for deep learning, and I bricked one of them and said, did an update, bricked one of them and said, something's wrong, and bricked the second one, and stupid. And the only way I could unbrick them was to load a Linux, a Ubuntu 16 onto a machine, because the code to force a reboot had to be. I couldn't get it running in 18. It just, it was. So there is some value in keeping old machines or old programmers around.
Yeah.
Yep.
I bricked a Arduino Shao, and I was able to unbrick it using a Raspberry Pi.
Hey, by the way, I still have some old Sun pizza box style 1 gig and 2 gig external SCSI drives if anybody wants any.
Yeah, do they float, or can you like put a long chain on them and use them for an anchor?
I was going to take them to a RARS Fest, but we haven't had a RARS Fest for 2 years now.
But that might be the kind of thing at RARSFest where at the end of the day, you have to decide, do I want to haul them out to the car, or shall I offer somebody $1?
You don't haul them out to the car. There is
you
no
offer,
decision there.
No, you offer somebody $1 to take it. Right.
I mean, the
price, -$1.
Yes. I mean, there's a collection of good magnets in there.
Yeah.
And the platters are kind of useful as coffee coasters.
Or art projects.
Well, it's getting towards my bedtime. I'm going to have to head out.
Me too. My wife wants to eat and she hasn't cooked dinner yet, so.
My dog wants to eat.
All right. Well, see you next time.
All right.
I will take the next month's slot to do the FPGA stuff.